Greetings, my name is István Bozsó. I'm a PhD student at Utrecht University and a guest student at the Faculty of Geosciences at Utrecht University. My co-authors and I are working on the development of a numerical geodynamic model intended to reproduce and help explain the evolution and formation of the East Carpathians, the Pannonian Basin and the seismogenic Rancia zone. In this presentation, I wish to give an overview of the progress and showcase an interesting recent finding, namely the formation of a retroarc basin, a consistent feature in nearly all of our models. First, I would like to briefly introduce the wider geological setting. The Carpathians evolved similarly to many Mediterranean subduction systems that are associated with slab retreat. The key difference is that in the case of the Carpathians, the back arc is at large distances from the subduction zone. In such systems, the subduction of a narrow oceanic slab is proposed as an explanation for the geological features, orogens, back arc basins that can be observed today. Contemporary geodynamic models set up with such narrow oceanic slabs are not able to generate the amount of slab pull required to achieve the previously mentioned features. To rectify this, the following model was proposed. In our model, a much wider oceanic domain is assumed that is made up of two components. A 700 km wide older oceanic domain that represents a former subduction system, which subduction system is inherited by our second component, the narrow 300 km wide ocean. This cross-section shows us the Pannonian Basin, the Transylvanian Basin, the East Carpathians and the Foxani Basin. The timeline of the events was the following. The upper plate subducted the oceanic slab and collided with the lower plate that can be seen on the right side of this cross-section at roughly 30 million years ago. After that, the slab retreated to its present subvertical position from roughly 30 to 8 million years ago. From here on, we will mostly concentrate on the slab retreat phase. The slab retreat is linked to the formation of the Transylvanian Basin. The retreat of the slab induced an astenospheric circuit beneath the present-day basin. This induced circuit or flow dragged the upper plate, forming the preliminary basin structure, which was filled up by sediments. The final stage was the exhumation of the basin. After that, the basin took up its present-day form. I would like to give a short overview of the numerical methods employed in this presentation. We employed numerical thermomechanical modeling using viscoelastoplastic rheology. The relevant partial differential equations are solved using finite differences and marker-in-cell methods. The effects of pyroscript was also included. In this slide, I will discuss the model setup. A 1000 km oceanic slab with a 100 million year geothermic age is flanked by two continents representing the upper and lower plates. The upper plate, seen on the right side of the model, is initially pushed with 10 cm per year for 9 million years. And shortly introduce the different phases that can be observed during the evolution of the model. We start out with the aforementioned kinematic convergence. After 9 million years, the model will evolve in a self-consistent way. It is in this phase that we see the self-driven subduction of the oceanic slab, the development of the retroarc basin, and finally the slab detachment. Here we can see the preliminary modeling results and the zoomed-in development of the retroarc basin. We see two composition plots for the reference model before and after slab steepening. We can see that the development of the retroarc basin is closely linked to the slab steepening. It is worth pointing out that the amount of sedimentation is not realistic and these are only preliminary results. This is a plot of the deviatoric normal stress after the slab steepening. The black rectangle outlines the position of the basin. The black curves in the asthenosphere outline the induced flow due to the slab steepening. It is important to note that this basin is a consistent feature in nearly all of our models. One possible interpretation of this basin is that this represents the Transylvanian basin. Due to the compression that can be seen where the retroarc basin is formed, we can interpret this as the result of the induced flow rather than extension. Our next steps will be to investigate the effects of sedimentation and erosion by adjusting the sedimentation and erosion model to be more realistic, and also investigate the effect of the convergence velocity has on the formation of the basin. In this figure we see the viscosity distribution and the answer to what drives our basin formation. As discussed before, the slab steepens, which induces an asthenospheric corner flow that can be seen on our figures. The flow deforms the upper plate, allowing a basin to form, and the basin is filled up by sediments, which further facilitates subsidence. These two figures are from different models, where we can see that the position of the basin is influenced by the dip of the slab. Not only that, but the presence of the basin is also related to the interface or coupling between the slab and the upper plate. Finally, I would like to conclude by emphasizing a couple of points made in this presentation. The reference model represents a very solid setup which we can build upon further models. Beyond that, based on multiple model runs, we can say that the retroarc basin is a robust feature that can be seen in many or almost all of our models. This basin can be interpreted as the Transylvanian basin, although further investigation is necessary to fully confirm that. The position and the presence of the retroarc basin depends on some other parameters, such as the dip of the oceanic slab and the interface between the upper plate and the oceanic slab. Regarding the future, we already have models running with better erosion and sedimentation settings and modified convergence velocities. We hope that with these new models we can reach our primary goals: shallow detachment that is similar to what we see today in the Rancian seismogenic zone, and the extension of the upper plate representing the Pannonian basin. Once we have these main features, we can carry out seismothermomechanical modeling to investigate the seismicity in the Rancian zone. And with that, I would like to thank you for your attention.